Children, today we will start with stereochemistry of SN reaction. Before we discuss about the stereochemistry for particularly SN reaction, we will learn about this term stereochemistry. It is the branch of chemistry that deals with the study of spatial or three-dimensional arrangement of a molecule. When we say three-dimensional arrangement, then it means configuration. How the groups attached in a molecule are arranged in three dimensions is known as configuration. For example, if I take lactic acid, that is 2-hydroxypropanoic acid. In this molecule, if we check three-dimensional arrangement, this one is central atom, that is carbon. 4 groups are attached to it. These 2 groups, that is hydrogen and COH, these 2 groups are shown by a straight line. That means these 2 bonds are bonds that are on the plane. This dark wedge, the group attaches OH group. It is the bond that is coming out of the paper above the plane, and this shaded wedge, that is CH3 group attached to it, this one is below the plane or away from the observer bond. This is three-dimensional arrangement. When we place a mirror, then we get 2 images that are mirror images, that is A and B. These 2 are the mirror images of lactic acid. Now, this branch stereochemistry, it is including 2 types of isomerism, that is geometrical and second is optical isomerism. We will learn about optical isomerism for stereochemistry. When we take beam of plain polarized light and it is passed through a solution of the compound for which we have to check the optical activity, optical isomerism. When we pass this plain polarized light to this solution of compound, it rotates this light in right hand side, that is RHS, known as clockwise direction, or left hand side, that is LHS, that is anti-clockwise direction. This phenomenon is known as optical isomerism, and the compounds or the isomers are known as optical isomers, also known as rotamers, or the optical isomerism also can be named as rotational isomerism. If I write RHS, it can be presented by positive sign, that is dextrorotatory, small d. And if I write LHS, that is represented by negative sign, that is levorotatory. Dextrorotatory, that will rotate the plane polarized light in right hand side, that is clockwise direction, and levorotatory compound will rotate this plane polarized light in left hand side, that is anti-clockwise direction. The angle by which plane polarized light is rotated measured by an instrument named as polarimeter. This polarimeter is shown in this slide. As per this ray diagram, we have taken first light source by which scattered beam of light is generated. When this light is passed through Nicol prism, this Nicol prism will convert the scattered light into plane polarized light. Now this plane polarized light is passed through the solution in which our compound is there, for which we have to measure optical activity and rotational angle. When this light plain polarized light is passed through the compound solution, it can, as per route A, it can rotate the light in left hand side, that is LHS, represented by negative sign. It is levorotatory anti-clockwise direction. Or either it may be rotate the beam of light, that is in RHS, shown by positive sign, that is dextrorotatory or clockwise direction. This levo and dextro is represented by a symbol L and D respectively. So when this beam of light is follow either A or B, that is LHS or RHS, then it is said to be the compound is optically active. When this beam of light is generated or obtained as it is, as shown by C, then we will conclude that this light is either not moving in right hand side or left hand side, so the compound is optically inactive. This complete diagram is showing this polarimeter, instrument that is used to measure the angle by which plane polarized light is rotated. Next we will learn what is the requirement for this optical activity. The requirement for optical activity is A. There should be chiral center or asymmetric center. Second, there should be non-superimposable mirror images. First, we will take chiral or asymmetric carbon. The word chiral is derived from chir, that is related to hand. When we check the symmetry of hand as shown in this figure, if we check, that is by vertical symmetry or either by any plane of symmetry we observed, in any case we will not obtain two equal parts. So we can conclude that this hand is having all different groups, that is it is chiral or asymmetric in nature. So this term chiral or asymmetric is related to hand. We can take some more example, that is first we have drawn this cone. In this cone there is plane of symmetry that is drawn by vertical line. Similarly we have taken square. Again it is symmetrical molecule. We will obtain two equal parts when we divide this square by any direction. We will get equal parts, so it was having symmetry in each and every direction. Next we have taken like alphabet A. It is having vertical plane of symmetry. Alphabet D, again it is having horizontal symmetry. So we can conclude when the group center atom is directly bonded to all different group, then it is said to be asymmetric or chiral. And when the groups are identical, then it is said to be symmetric or achiral. So all these examples that we have drawn, that are symmetric or achiral centers. Now we will take some examples of chiral center. We will put star on the chiral carbon. So in first case we have taken the example, that is lactic acid. This is stirred carbon that is directly bonded to 4 unidentical groups. Second example, again 4 unidentical groups are there, that is Cl, I, Br and H. In next example, that is 2-pentanol. In this molecule, methyl group, propyl group, OH and H, that is 4 unidentical groups. So again it is having stirred carbon. In next case, that is 2-bromobutane, stirred carbon is directly bonded to 4 unidentical groups, that is hydrogen, bromine, ethyl and methyl. Next we have taken glyceraldehyde. In this molecule, stirred carbon is directly bonded to OH, CHO, CH3 and H. This three-dimensional structure was first observed by Lobel and Van 't Hoff. So in overall, we can conclude that chiral center or chiral carbon, it is bonded with unidentical group, then it is chiral or asymmetric carbon, and the property is known as chirality. Next we will take second requirement for optical activity, that is non-superimposable mirror images. When mirror images of chiral center are not superimposable, then this is the second requirement of optical activity. For example, if we try to overlap our left hand to right hand, our hands are identical to each other, but when we will place mirror or when we put our left hand to right hand without rotating, then we will observe that these two hands will not be superimposable. We cannot wear right hand gloves to left hand glove. So this is like non-superimposable mirror images. We will take some more example by which we can explain this term non-superimposable mirror images. Like we have taken 2-butanol. This plus sign is showing rotation, that is clockwise, dextrorotatory we will write it. So this is stirred carbon that is directly bonded to 4 unidentical group, that is CH3, OH, C2H5 and H. When we will place a mirror, then we will get the mirror image. Now these two mirror images are like left hand and right hand, and these two mirror images are not superimposable. But remember, when I will rotate this mirror image, that is A or B, any of the mirror image, when I will rotate it by angle of 180 degree, then I will get superimposable mirror image like A and C. As you can see, this is A and the next one is C. These two are identical, completely identical mirror images. C2H5, that is below the plane, and hydrogen. These two are left hand side of the plane. Similarly in C structure, C2H5 and H, left hand side of the plane. OH, right hand side in both the cases, and CH3, that is planar bond. So these two are identical. So these two images, that is A and C, by rotation of 180 degree, we will get that are superimposable mirror images. Whereas A and B are non-superimposable mirror images. So this compound, that is 2-butanol, it is justifying both the requirement, that is chiral carbon, and second, non-superimposable mirror images. So it is said to be optically active, and these two pair of non-superimposable mirror images, that is A and B, are known as enantiomers. Next, third example that we have taken, that is isopropyl alcohol. In this isopropyl alcohol, as you are observing that we have not stirred the carbon atom. The reason is that the center carbon atom is directly bonded to 2-methyl group. That is, if 2-methyl group are there, then we will say 2 identical groups are there. So it is not having stirred carbon. But we can draw the mirror images as shown. These two mirror images are not superimposable, but it is not fulfilling our first requirement, that is chiral carbon or chiral center. So it is optically inactive. We can take one more example. This is our stirred carbon bonded to 4 unidentical group. Mirror image of the same compound is drawn. First is dextrorotatory, second is levorotatory. So this is enantiomeric pair. These enantiomers will show similarity in physical properties like melting point, boiling point, density, refractive indices, etc. If I rotate this dextrorotatory structure by the angle of 180 degree, then I will get the third structure that is identical to second structure. These two structures, second and third, are superimposable. Identical structure. There is chiral carbon, but these two superimposable mirror images by rotation of 180 degree not justifying the requirement of optical activity. We have to not rotate the compound. As it is, we have to draw non-superimposable mirror images. Next, we will learn about some more terms in stereochemistry, that is racemic mixture. If 50% dextro and 50% levo compound are obtained, then it is racemic mixture. Overall rotation in racemic mixture is cancelled out, so the rotation is 0. We have taken one molecule, that is tartaric acid. There are two stirred center, two stirred carbon atom, that is carbon 1, CH3, OH, COH, and fourth group. All the four group are unidentical. Second carbon atom, that is stirred carbon, OH, CH3, COH, and this one is the fourth group. So there are two stirred center, two stirred carbon atom. There is plane of symmetry is there. We can compare this plane to the mirror, then we will get two mirror images. These are two mirror images. So in first structure, if the rotation is from OH to COH, that is anti-clockwise, 50% levo is there. And in second case, OH to COH, the rotation is clockwise, that is dextrorotatory. So within one molecule, we are getting 50% dextro and 50% levo. So overall rotation is cancelled out. There is optical activity requirement justifying that the stirred carbon is there, non-superimposable mirror images are there, but still it is optically inactive due to this 50% dextrorotatory part and 50% levorotatory. Overall rotation is cancelled out. Similarly, if I draw for lactic acid, 50% dextro if it is, or 50% levo it is, then it is said to be racemic mixture. Next term, that is inversion in configuration. We have already discussed about inversion in configuration and retention in configuration while we have differentiated between SN1 and SN2 reaction. If attacking group attack to opposite side of the departing group, then it is said to be inversion in configuration. And when attacking group attack to the same direction of the departing group, then it is said to be retention in configuration, generally observed in SN1 reaction, SN1 mechanism. Now we will take some examples for stereochemistry of SN reaction. First, when departing group is present at symmetric center, then it results retention in configuration. For example, we have taken 2-methyl butanol. This is first carbon atom, that is stirred carbon atom. 4 different group are there, that is CH3, hydrogen, C2H5 and methyl alcohol group is there. Now second carbon that we have circled This is our symmetric carbon atom. Two hydrogen atom are there. So this carbon atom is symmetric. This is the OH group, that is the departing group. When this is treated with dry HCl, OH group is departing from symmetric carbon atom. So Cl will come from the same direction, attack from the same direction of the departing group, and it results retention in configuration. Our configuration for the reactant was minus, and for the product again it is minus, that is -1 chloro-2-methyl butane. Second example, when departing group is present on stirred carbon, then it will be inversion in configuration. We have taken one example, that is +2-chlorooctane. Stirred carbon atom is shown. The Cl atom, that is our departing nucleophile, it is present on stirred carbon atom. In presence of aqueous KOH, the nucleophilic part is OH minus, it will follow SN2 mechanism. Both the reactant are attacking. So the Cl group will depart. As soon as Cl group will depart, OH minus will attack from the opposite direction of the departing nucleophile, and it results inversion in configuration, that is +2, the product is -octane to all. Third example that we can take, that is when optically active halide, if it go for SN1 mechanism, when optically active halide go for SN2, then there is inversion in configuration. But when optically active halide go for SN1 mechanism, then it will result racemic mixture. Why this is so? When we take this optically active halide, that is +2-bromobutane, this is our stirred carbon atom. In presence of protic solvent, it will generate the intermediate carbonium ion. This carbonium ion is sp2 hybridized. Geometry is planar trigonal. This intermediate is planar. So the attack of nucleophile is feasible from both the directions. That is from the direction of the departing group and as well as opposite direction of the departing group. So it will result plus butane to all 50% levorotatory and minus butane to all, that is 50% dextrorotatory. So in overall, we can summarize, if SN2 mechanism for optically active halide, then there will be inversion in configuration. And when optically active halide go for SN1, due to this intermediate planar sp2 hybridized carbonium ion, the attack is feasible from both the direction. It will result 50% dextro and 50% levo, that is racemic mixture. So we can summarize in simple way that when the attacking group is attacking in the same direction of the departing group, that is retention in configuration. When the attacking group is attacking to the opposite direction of the departing group, that is inversion in configuration. And when we will obtain 50% A and 50% B, that is racemic mixture.